Go ahead.
Great, thank you very much. Yes, so welcome indeed everybody to today's Software and Computing Roundtable, which is on analysis tools. We have three excellent speakers lined up, covering lots of different aspects of what analysis tools actually mean and how you put them into practice for doing a real analysis. But before we begin this more substantive content of the meeting, we have a couple of announcements. So the first one is from Eduardo, who's just going to give us a brief introduction to PyHep, which is one of our exciting upcoming events. Will you share the slide, Eduardo, or do you want me to put it up?
Okay, yeah, I can share. I wasn't sure. There you go. Can you see that?
We can indeed, yes.
Okay, so yeah, thanks very much for allowing me to give a short advert here. So it is indeed on this PyHep series of workshop, Python in hydrogen physics. Of course, it's not just hydrogen physics. That's the whole point. Really, is particle physics in general, and we try to engage with as many communities as possible. So just to say that the next incantation is taking place in July, so in about 1 month from now, and so give you an idea. There's a few plots here to show that we're having a very nice group of communities represented. Yes, indeed, we have a very large presence from LHC, not the least because we're talking about the huge collaborations. But you see that 45% or so of the people registered so far, in fact, are not from the LHC. And for example, communities such as neutrinos or even research institutes and some other are very well represented again this year. In fact, neutrino is new, so I'm coming to you to present this because the workshop, being Python in general for analysis, with the whole ecosystem that has evolved enormously over the last 2-3 years, this might be of interest to many of you, and we certainly would be super happy to see even more people from your communities. At the bottom there, in those two colorful pie charts, you can see that there is already some representation, in particular from JLab and BNL, but if there is more, then the happier we will be. On presentations, not just participation, but if you actually would like to present something on, for example, what packages you're using more from the Python ecosystem, or how you're doing analysis in Python and so on. So this is pretty much open-ended. We have several types of presentations. One is long tutorials. The other one is kind of standard notebook presentations. We try to have interactive notebooks as presentations, 20 plus 10 minutes for discussion. And then we're also going to have, in the end, the session for very short, a bit longer than lightning presentations for something that maybe is not yet as solid as possible as you would like to, but as a hello world, if you want to say, listen, I'm preparing this thing, this is still a work in progress, but this seems interesting, I would like to share with you. We're going to have and accept a few of those short 10-ish minutes presentations. So by all means, do get in touch with us, and we very much look forward to seeing many of you participating in one way or another. That's all I wanted really to say. Thank you very much.
Yeah, thanks so much, Eduardo. I have to say that PyHep 2020, the virtual one that we held last year, was, for me, one of the most interesting things that I did last year. It came out really well. This event actually as a virtual workshop. It worked very nicely. So I do encourage everyone to get involved there. So thanks for that. And we have a second announcement. It's from Marcus about the EIC Software Town Hall.
Thank you, Graham. So we have on Thursday the first EIC Software Town Hall. I hope you, sorry there, it says that there's some problem with the screen sharing.
I'll throw the slide up for you.
No. Okay, thank you. So we have on Thursday the first EIC Software Town Hall. The motivation here is that all scientists at all levels worldwide should be able to actively participate in the science for the electron-ion collider. And that means that we need to understand the requirements of the community on the data analysis softwares, on the workflows first and foremost. And in order to do that, part of our motivation is to have then the software town hall, where anyone has chance to share past experiments, also just requirements for EIC software in an open environment. I link here the Indico page, and there are also some instructions for those who would like to share some slides, whom to contact, so that this is all then being put on the Indico agenda. That's all. Thank you very much.
Yeah, thanks, Marcus. It's always good to hear about these events. It's really an important one to go along to. So Grant, yes, thanks to you both for that. And let's now move to the main part of the meeting. So very pleased to introduce our first speaker. That's Jan Bernara. He was born in Mainz in Germany and also studied physics in Mainz. Then was a postdoc for quite some time at MIT, working on Olympus and dark light. And since 2018, he's moved to Stony Brook University, and he's one of the principal investigators for the EIC's streaming readout project. And he's going to share with us some of his thoughts on analysis tools. So without further ado, I'll let you take it away, Jan.
Thank you. I hope you can hear me and see my slides. Take that as a yes. Can you hear me?
Yes, I muted myself.
All right. So yeah, thank you for the very kind introduction. So just to frame this a little bit, I'm really, the physics side of me was socialized in these small and mid-sized collaborations, right? So growing up in Mainz and studying there, the A1 collaboration isn't that large, right? And it's actually quite special because it's one of the very few collaborations I know which are not using root. So they have their own custom analysis package, and it's C and C++ based, and it actually predates most of root. And they use this and develop this. And actually for the next generation of experiments, they are building a new one, again, not so much on root, just what they are used to. When I came to Olympus, I actually picked up root and wrote an analysis framework on top of that, which was used in Olympus. And it's also now used in Darklight, TPEX, Muse, and Track. And Track is actually an experiment where I'm not involved in. So it's not only me which is pushing this. It's certainly nothing for a big experiment, but it taught me some lessons on what to do and what not to do, right? It's a thin layer on top of root to make some things a little bit easier. The nice thing about it, it actually compiles on all Linux distros and macOS without too much hassle. So it doesn't need a Docker image or so to get started. What I want to comment on this here, and that's maybe a big difference between HEP and nuclear physics. The nuclear physics students often start like as an undergrad or a graduate student at smaller experiments, and then later join something like EIC as a postdoc, right? So not only focusing on these big experiments, but having something which can be used in the whole range, or will be used in the whole range of experiments, can really help to exchange students between different experiments and giving them a quick way to be productive without having to relearn everything, right? So yeah, I'm also the PI of that streaming readout thing. So the other perspective I have here is actually from a streaming readout perspective and what that might change in the way we do analysis. And that's actually where I want to start with. We always talk about events, right? And what we actually mean most of the time are the physics events, right? Something which is causally linked, right? It's a causally linked chain of things happening, right? A particle is shot into a target, it bounces off, stuff happens, stuff comes out, right? It's causally linked. And that's what the theorists would think about, right? And a Monte Carlo generator normally produces, right? Typically. And that's what we need in the final physics analysis, because that's the thing we count, right? It's all counting. We count how often this happens with these specifications. That's a bin, right? And then we do things on that. But on a DAQ side, we have a different type of event. right? That's what we have on tape, on disk, or whatever, which is not linked by causality, but by coincidence, right? It's things happening at the same time. So typically we associate a trigger with it. So if you have a trigger, that produces an event, right? Or maybe multiple triggers fire at the same time and they all produce one event then, right? And in streaming readout, we can emulate this, right? We have like time buckets and everything in the same bucket is then an event, right? Or we may associate it with a bunch crossing, right? So the same bunch crossing is an event or something like that. But that actually breaks down at some point if you have detectors which are really, really long, long conversion rate times. So these things are obviously not the same, right? A duck event can actually have multiple physics events plus noise, which we are not interested in, or it might have no physics event, might only be noise, right? And especially if you think about streaming readout and use these definitions of what an event is there, a physics event can actually span multiple DAC events, right? And typically our analysis software is actually driven by these DAC events, right? We read event by event from the file, which are DAC events, and then process them and sort them. And the reason for that is that the data is stored this way. And it might not actually make much sense to do it this way if you go away from the trigger where that's a natural storage. Right? So the decision what belongs in a physics event is actually an analysis task. This is nothing the DAQ should do, right? And it might actually be really high level, right? Especially if in streaming readout, you have really long detector times for something like a TPC and fast detectors like a timing detector, right? Associating this all together, right? And overlapping events and all of this. This is a really complicated task which should not be solved on the DAQ level. This is really a high level task. And if you think about something like a delayed decay of dark matter, right? It might be really something where you think about only 10 years after you took the data, you come up with a channel where you can look for, or what you can look for in a streaming readout thing because it's on tape, where the definition of an event doesn't make any sense because now we have a lot of time between something happening and then seeing something. And analysis tools actually need to support this difference between what's on tape and what we physically interpret as an event. And this should not force this eventification early on, right? This should really be something organically defined in the analysis. If you look at streaming readout, what comes from that is that you decompose your data into streams, right? And each element of a stream is then the same or a similar type, right? You can multiplex these streams and have a stream of streams or something, but in principle, you can say, I have here a stream of, I don't know, TDC hits in this detector or IDC waveforms in this detector or whatever, right? And the only thing they have is they are time ordered and time stamped. So the association between different detectors runs over this time. The whole analysis is then a directed graph. It should be acyclic with calibrations. This is not completely true, but in principle, you can write it down as a network, right? And each operation there, each node takes some input streams and then adds a stream to the output. Right? You can maybe drop other streams if you don't need them in the output anymore, but that's essentially what it does. It's very similar to, if you think about it, like functional programming, right? And this can actually drive you quite a long way, right? So instead of having a stream of hits, you could have a stream of tracks or a stream of physics events. Right? And they happen each other after each other, right? So they're time ordered, and you can like look at this stream of events, and you can build complex things from that. But you still have the concept of a stream where everything is just time ordered. And it's actually, if you program, right? I always get really annoyed at patterns like this, where you have, okay, I do something for all events, but in an event, something could be there multiple times. So I have to iterate over all hits and then I do something. And if you think about that, how to do this on, let's say, a vector machine, right? Or HPC, where you want to stream a lot of hits through fast, having these events as nonsensical delimiters really just stops you, right? You just want a list of all hits, right? Time ordered, and push that through. So for example, if you look at TPC reconstruction, there would be a first step where you have as an input the TPC hits, and at the output, maybe something like track stubs. So tracks in the TPC, and if they don't cross the readout plane, you can't resolve the projected axis. So they have one dimension unresolved. Right? And parallel to that, you have a different detector which gives you timing. So maybe waveforms from an ADC, and the output of that would be timing detector timestamps. And then the third step would take, or the second step, because the other one are parallel, would take the outputs of these two, combine them, and get full tracks out. So what we see here is, if I change one of these steps, I don't have to redo the other steps, only the steps which are down the pipeline. So if I change the way I also associate checks with these timestamps to get full tracks out, I don't have to redo the other two steps. That gives you actually an opportunity, if your code is structured like this, to cache these intermediate results very aggressively and really save in your development time of these algorithms. Right? Because you don't have to do the first steps anymore. You have them. You only optimize the last step. So what are the effects of this on storage? So you don't have a massive event. You don't build a full event where all the information from that event is next to each other, right? You have semi-independent streams. They are only like associated with the timestamps, but otherwise they are like internally complete for only a part of a detector or one detector element or whatever. And that could. So the host muted me. I don't know if that makes sense.
That was my mistake, Jan. Sorry, I was trying to meet somebody else and the participant order switched in Zoom in that very annoying way. I ended up.
All right. Okay. So let me continue. So the data might be in multiple files, and your analysis tools actually need to be able to find the right data, right? But it also means that you don't have to load all the data. You only need to load what you actually need for that step. Right? And especially if you have a very heterogeneous environment where some nodes maybe have GPU accelerators to do tracking and others have a lot of RAM to do this other thing, and other nodes are specialized for something else, right? Not having to distribute all the data to everything is actually really nice. And you only write out what is new, right? You don't rewrite all the events. You don't have to copy the information forward. It's just a new stream. It's just a new file living in your data lake or whatever data warehouse, whatever you have. This also kind of obliterates the need for data summary tapes, because these are just a different selection of these streams. So instead of having no DSTs, you actually have custom DSTs at any level, because every node can specify, right? Every process can specify, I need this, this, and this, and this as input, which can, if it's always the same, can be easily cached, right? And distributed without having everything. You only need that. But you can be very like granular on what channels you actually need. And the discussion of what, oh, I need this in the micro DSTs, or I don't need this, or this is getting too big, right? This goes away. You only take what you need. And if somebody else needs something else, they take something else. So the effects on compute are similar, right? You only load what you need. So you only have to transfer the data to the nodes, which is actually processed by the nodes. Only write what it's new, the same thing, right? You only have to transport back what they actually produced. The data structures tend to be simpler, which makes it much easier to stream it through high performance computing elements, right? GPUs and stuff like this. The data is actually more homogeneous because it's more similar. So if you apply some compression on it, that might actually be improved. And you can really aggressively cache intermediate results, right? Even if you say, okay, this should not be saved during like a development cycle of code, right? I mean, how often do you compile and run a tracker until it actually works, right? You can cache the input of that, and don't have to redo it, and it can look at this quickly. So that really makes a lot of stuff a lot faster dev cycles for that. So also it has some effects on how you code, right? It naturally decomposes your analysis in individual semi-independent tasks. So if you have a lot of people who can actually write code, if you're in that nice situation, it's easy to distribute these things. And the data structures actually define the interface, right? There's no API definition. It's the data which is shared between those. You can exchange parts. If you say, okay, I have this tracker, but now I want to try this other tracker, it's easy. We just exchange the node, right? Instead of having some monolithic analysis thing where sooner or later ripping something out and replacing it is always a lot of work, right? It's naturally separated. This also maps trivially then to responsibilities of groups. So the organization is easy. And it really contains the effects of code breakage, right? If some node doesn't work anymore in the compiler, all of the rest can still work and it can be compiled, right? And it can be worked on. And you don't have just a monolithic non-compiling object anymore, right, which you can't run, right? You just can't use this one node, but everything else you can do, right? So obviously, if you have a typo in there, right, you might not be able to make something. We need tools to actually organize this data. This is really different from what we normally do, right? Where we have one big run file for a run period or something for a run, right? There has to be some logic to actually do this caching to get these benefits. You want to be aware of the data locality. If you don't put it back into the lake, you might want to say, okay, these nodes operate sequentially on this data. You might want to have them on the same node where it's locally saved, right? And I strongly believe that it's really important to allow for a disconnected mode where a student can be on his laptop, his or her laptop, have some data on there and work on that for like developing code and testing algorithms and all of this without having to log into a central server or whatever, like being on a train or whatever on a flight, and should be able to do work. Not everything, but some things should be possible with that. So switching gears a little bit, should you optimize for users or developers? And I think there is a real difference between HAP and nuclear physics, or between big collaborations and small collaborations. In small collaborations, all your users are developers. You don't have enough people to not say, okay, or to say, okay, you are only doing analysis, right? We provide all tracking and we have fully final physics events. You only look at cuts, right? That doesn't happen. And typically we need more developers, right? So we want to take, if we have users, take users and make them developers. So we have to make sure it's easy to become a developer, right? And some things for that is, for example, do not adopt a REPL model, right? I think that just produces bad code. If it's too big, you quickly, I mean, it's spaghetti code, right? So that doesn't put people into the mindset to decompose a problem into functions and procedures and stuff like this, right? They just write it from top to bottom, 1 page, 2 pages, 10 pages until they are done, right? And you don't want that. So that's a really bad thing to train them with, right? And using a web browser is a bad replacement for a proper IDE. I realize some IDEs are actually web browsers in the back, but right, you know what I mean, right? So that's good for small things, but there is a transition to something which is more complex. And if you train people the wrong way to approach a problem, it's really hard to untrain that. It's really important to avoid hard transitions in that journey from a user to a developer, right? So for example, Python and Jupyter are great. It's really great for users, but you cannot write high performance algorithms in pure Python, right? All of the code in the backend is written in C, right? And if the libraries which exist don't fit your data very well, at some point you want to write that in C to make it fast. So you have to learn a new language, and you have to learn, which is hard enough, right? And you have to learn how that new language and Python interfaces, which is not the most simplest thing, even if there's a lot of improvement. So you make it a lot harder for somebody to go from, okay, I can do something in Python, into, okay, now I can change the algorithms behind it, right? It's just the steep learning curve that you have to jump over, which you will lose a lot of people. Same with Singularity and Docker. It's really great to get started with this, right? But to really have a nice development environment, right? So what is my editor? How do I get data in? How do I compile stuff if everything is pre-compiled? What do I do there, right? It's maybe better to have the pain once in the beginning to set everyone up with an environment which then travels from I'm just a user to I'm a hardcore developer. And I don't think this is unsolvable, right? It's more work in the beginning, so onboarding will be harder, but after then, it's much more straight line. So how can you avoid these transitions? Give them a complete setup, right? Make them compile stuff. Don't give them macros, right? I think give them maybe a template to start with, where they only have to change a couple of lines and then it compiles, and make that easy to set up. But don't train them in something which doesn't give them a way forward. I think a lot of people were ruined by root macros, right? Especially because Sint allowed a lot of stuff which was not working in then compiled code. It's better now, but this really was a problem, right? Stay in one language. Pick one which really travels all the way. So what language to use? And I think the answer there is modern C++. I think it's too late for Rust, for EIC, and I think actually in general, there's just too many people knowing C and C++. There's also, if you look at the hardware side, right, there's System C, OpenCL, all of these languages which are really, really C-like. So somebody who speaks C or C++ will have a much easier time with those than somebody who is writing Python, right? And I really think Python for most things is too slow, except for like the high level puppeteering of stuff, where it's great, right? But downside is you have this transition. The other thing you avoid with this is you avoid the black box problem. And I've seen that a lot. All documentation lies. Even if you put a lot of work in documentation, the documentation will not be perfect. I can show you a lot of things, for example, in the root documentation, which is otherwise really, really good, where you really scratch your head and where it's just plain wrong, where you actually have to look in the code to see what the code does, right? And even if you have the best intentions, right, it rots fast. And in the best case, it only documents what the author thought the code does, not what the code actually does. So having the ability to read code is really, really important, right? They need to be able to look at lower level code and say, this is different from what it's written, right? And if they do that more and more, they will become developers. So how to get people to use your stuff? If people are using something else, you already have lost. It's really, really an uphill battle to convince people to switch because they are not interested in it, right? It's not like they are computer scientists who say, okay, I want to try this other software package because that has interesting concepts, right? They want the physics out. So it's really an uphill battle. And you can only win if you have essentially feature parity with what the people are using. Right? If there is something halfway crucial missing, people have a reason to not use it and they will not use it. Yeah? It must be as easy or at least similar to use how the old code is. And you need some standing point why it's worth to switch. And the standing point cannot be, but it's easier to maintain. Right? It must be something where the user has the benefit of it. Immediate benefit, not in 10 years. And I have seen this in Mainz. We had somebody write a new version of a code and it never reached feature parity. It was well designed, really, really well designed. It was a really good design, but it never reached feature parity was had before and people just forgot about it. Right? So just to end it, I ended with a root rant. because I think there's actually things to learn from it, right? So do one thing and do it well. I'm really not a friend that root wraps every library under the sun, right? It's not systemd, it shouldn't do that. It should maybe, I mean, why does root have a machine learning library and a histogramming library? These are really not similar things. This could be different, well-capsulated projects. And that makes it also easier to use different ones if you don't like the root histogramming, right? Just exchange it with your own library. And if the interfaces are well defined, that should be possible. And that's typically not the case. Please get rid of global state. This was a good idea to get people on board from the POR days, but global state is the problem, right? Because it's magic, it hides stuff, it hides interaction in the background people don't know about or assume that it works, and then suddenly it doesn't work. Or I had the problem, for example, that I wanted to load a GDML, and the default way would always kill the GeoManager and produce a new global GeoManager with the loaded GDML. So how do you load two at the same time, right? Wasn't easy. You can figure it out. It's no better, but stuff like that. Think about names and the overall structure. So for example, if you have a th1 clear, can you tell me what that does? Right, so it's a histogram. And if you don't know better, you would probably assume that it clears the histogram. But it doesn't, because the clear is actually from a t named, which is a parent of the th1. So it only clears the title and the name, right? And I know people who have fallen for that. So obviously the right solution would be to overload clear to actually clear the whole histogram, or use a better name, right? Clear name, clear title, whatever, right? Despite I'm not sure how often you ever have cleared the name and the title and not set it new, right? So maybe it should just go away. Don't be completely brain dead. For example, the t timestamp has a function get time, gives you back an integer, which is either 5 or 6 digits. And each digit, if you write it as a decimal, codes like the lowest two digits code the second, the middle one the minutes, and the highest 2 digits code the hour. There is no use for this, right? If it could be a string, it might be useful, right? But there's no like numerical sense to have this as an int. It's not like Unix time epoch or something. And generally from that, I would say avoid magic. Every magic thing you have where something is automatically done really nicely, right, without description how it actually works, means that the people will not look under the hood what is actually happening. And at some point, your magic will break, right? And then it's not clear how to fix it. So avoid that, make it clear what's happening. You can have helper functions to encapsulate functions, but make clear what steps are actually done and how it is done in the background. All right, that's all I have.
Yeah, and thank you very much. That was a talk with lots of interesting things in it. So yeah, let's open up the floor to questions. And the first hand raised is from David. So go ahead, David.
Yeah, so thanks, Sean. This is great and wonderfully provocative. There's so many things that we could talk about. The one thing I wanted to ask about, though, is you started off a lot on the streaming readout, and you made some very good arguments for that, of saving all the different streams. But one thing that kind of concerns me a bit is that it seems like you end up with the potential of using up a lot more storage in order to save all of those streams if you're not doing something to slice out bits of time that don't have anything interesting in there. And sure, we know that the people who build the detectors are going to want to spend money on the detectors, and they're going to balk at spending a lot more money on storage for this. And I just wanted, maybe you could respond to that.
Well, certainly, I mean, the primary data, right, is what it is, right? And we probably, I mean, this will be reduced to some amount that we can write it back and then have it, right? And that data will not be touched, right? We won't delete this or anything. As soon as it hits the tape, you probably have to keep it as is. Everything else after that can be all temporary, right? You say, okay, I have this cache pool here, right? And the same way a CPU kill stuff which is too old or not used, right? You know how to produce it from the original data, right? Each chunk has to be recorded somehow. And if it's not cached anymore, okay, then we have to redo it. And this will automatically, the stuff people work on will be in the cache, and stuff people don't work on anymore or is old will be flushed from the cache, right? And then of course you can like pin things where you know, okay, I don't need it now, but this was really expensive to do. So we might need it in a year. So we pin it and maybe write it to tape or whatever, right? And because it's time ordered, right? There's no reason not to kill time segments where you say, okay, in this time segment, there's nothing interesting, right? So saving nothing is cheap, right? So I think this could be workable.
Thanks. We have another question now from Andrea.
Yeah, if you can get back to slide 10, I really don't understand your example here, because it is true that in some cases you may not need the inner loop, but in fact, eventually when you get to do an analysis, you need to. I mean, in the sense that you want to have the event by event. I mean, there are boundaries. It's not just about looping do something on the hit and then having the double loops. The point is that you may want to accumulate the hits per event, and then, I don't know, just draw the number of hits that you have per event.
But is that actually true? Do you want to accumulate per event, or do you want to accumulate over a certain time period? And I think it's mostly time period, right?
Perhaps it depends really on the domain here. But
yeah,
I think eventually, even for experiments where they have long integration time, you may want to get back to what happened, and so to think of in terms of events. No?
Yeah, but I think that you do that really, really late in the game. So for example,
that probably depends a lot in the domain. I mean,
sure, but
probably I mean, for sure. For example, for LAC experiments, this is not really the case. I mean, even if there are detectors that are integrating over a long time, I think that you immediately want to, or pretty soon in the chain, you want to get to the event granularity.
Well, I'm not so sure about that. I mean, let's say a TPC window goes over 10 events. So do you duplicate the TPC data then for the 10 events? Or do you have...
The point there, for example, for many LAC experiments, you have a trigger acceptance that is so low that the chances that you want to store 2 events in a window of 10, it's very little. So
yes,
basically you put the full time frame in the event you save, and that's it, and there is no duplication.
Yeah, in that case, this all goes, I mean, then there's like 100% overlap, right? You say, okay, my timestamp is now just my bunch number, right? And everything in one has the same timestamp, and then it's the event number, right? In some sense. But in EIC, this is not true, right?
No, I understand. I'm saying it depends a lot on the domain.
Probably. Yeah, sure. But I mean, if you are so low, right, then you have a triggered readout, and at a triggered readout, right, it makes sense to be driven by the triggers, right? But if you go in a regime where a triggered readout is actually, you have more than one trigger event, right? In that case, a true event is mapped to one DRQ event, right? There might be not ever always a true event in the DRQ event, but it's really rare that there are 2 in there. But as soon as this is not true anymore, as soon as your event density goes up, right, you might want to go away from this event-driven and want to do something.
But eventually, even in the case you integrate, eventually you want to resolve the events for making the analysis.
But that's really at the end, right? That's really when you start doing physics stuff, right?
Okay, thanks. I think we should probably move on in the interest of time to some other questions.
Oh, but I'm riled up. I'm angry. Oh, it's okay. Yeah. No, I'm kidding. Let's go.
No. I was thinking
one more question by Wouter in the discussion.
Yeah, there's a question from Wouter. So, do you want to read your question, Wouter, or shall I do it for you?
Oh, you can read it.
Okay. So, Wouter commented, in the context of Jupyter, you said you force users to learn a new language by using Python, paraphrased. New users come into the field with Python, which is very much my experience now, as the language they know, and C++ is the new language. shouldn't we take advantage of what languages users already know?
Yeah, that's a very good point. And my argument is there, if you, so the back end will always be something not Python, right? I don't believe that you can really write the full analysis in Python and get any like performance out of it. So I would argue that especially in smaller collaborations, these people will have to learn C++ anyway, right? Because at some point they have to look under the hood, they have to write something new in the backend. So yes, we lose that and we force them to do that maybe from the beginning, and that's a problem. But the benefit of doing it early is that if somebody knows Python and then has to learn C++ to look under the hood, he not only has to learn C++, the person also has to learn how that C++ interacts with Python. So you make the problem, you made the entry easier, but made then the next step harder. And now it depends. How often do you have to take the next step? And I think in HEP, where you have very dedicated, I mean, I'm not in HEP, so maybe I'm talking out of my ass here, but it seems that you often have dedicated groups to write the backends and way more people who write the high level analysis, right? Who do the cuts in Python and all of this. And then it's good to start with Python, and there are not so many people who have to do the transition. But if your group is smaller, where everybody has to make that transition, I think that's a price you rather want to pay early, right? Where simple analyses can be simple C++ programs, and it's easy to learn simple C++ programs. And then you have this like slow rise in the complexity, even if the first step is a little bit higher.
Yeah, I'm interested in that. That would maybe make the comment that a lot of the C++ that was written for the LHC was a bit of a disaster when Coverity looks at it. So somehow C++ is quite a hard language for people to program in. Maybe that's something that we need to evolve. However, let's move on to Eduardo. Your comment?
Yeah, interesting discussions, and yeah, I could comment on Python, but let me start by commenting on the C++ for once. I think the discussion and the points that you're making, we're going to have it, and we're already having in some sense for GPU programming, even if you stay just within C++. And there, I agree with you that there's probably a difference between very small experiments and very large experiments where you can really dedicate a small team of truly experts, and then the bulk of the analysts will be talking about between a handful of folks, for example, in LHB that can write the GPU code for our first level trigger, and then behind, and you have 200, 300 analysts that are absolutely not C++ experts, and they probably will never need to become C++ experts on the lifetime of their PhDs or even postdocs in many cases, right? So I think that there's indeed, I think there are a lot of good points, but we should always specify, as you have been doing, the differences between small experiments and big experiments. And I think on the Python, what you mentioned on Python side, the same goes there as well. In a small experiment, I can well believe what you're saying, but again, in a bigger experiment, you should never underestimate how much time, in fact, the typical analyst will be playing with interactively with a small amount of data and with small things for the analysis. So if you integrate over the whole course of an analysis that can take even longer, more than a year, the performance of that piece of code that we'll be working with, which is totally different from the DAC code, for example, is actually dominant. So and the fact that you have to iterate and so on. So in the end, even if you had something that it was, I'm being almost aggressive here, affected too slow, it will not. It will not. You could do the exercise, but it's very difficult to quantify. But I'm pretty sure that you would not. It would still be less compared to the time people will waste making writing bugs and reiterating of the data because they have forgotten variables and doing all kinds of have checks and investigation of the data, because data analysis is not something that you tick a list and you say you do A to Z, and when you're done Z, you're done. You have no idea how to reach that Z, right? And the M and N and so on letters are something that you only discover as you go along. So I think there's a lot. This is an endless discussions. I think you have got a lot of good points, but again, we should always see it within the right scope.
I think it's faster to write Python. I'm not sure if it's actually less error bound to write Python compared to really modern C++. The main issue is that Python has no type system, right? So, I have certainly run a lot of Python code which fails in the last step because I didn't see that the type is wrong, and it just fails on runtime instead of compile time.
It's interesting how, and then I will shut up afterwards. It's interesting how the languages are evolving, because now we are seeing, certainly in the software packages and libraries that people are across the community are delivering, you see more and more type checking in those packages. Yeah. So you have a bit of a middle ground from all sides, because also C++ has evolved enormously. So things become a bit more fuzzy, but
but it's not on compile time, right? So you can feed SkyPy, you can feed in a number which is not the same type, and it will only fail on runtime, right? And a compiler might see that, right? So I'm not really a big fan of C++. So I think if we would have ideal times, maybe we would look at Rust or stuff like that, which would take out a lot of bug classes. And it's not maybe the most easy language to learn either. Or I would look at a Python equivalent which doesn't have the global lock, right? So that it actually can perform. But I think that on the back end, C++ has so much momentum from people being able to write it. And it's the only language right now which is common and performant, right? That's why I'm looking so much on C++. And the overlap with OpenCL, System-C, all of this, right?
Yeah, this is a super interesting discussion, but I'm also conscious that the clock is ticking, and we have to be time efficient ourselves in the meeting. So remember, we do have the live notes, so people can perfectly well take advantage of putting a few more comments in there if they would like to carry on the discussion. But thanks very much, Jan.
Sure.
But I think we're forced to move on, the pressure of time. And we're going to move to Andrea. Andrea's a CMS member, a long-standing CMS member, physics coordinator, who works at INFN Pisa. And he's one of the chief architects of the CMS data analysis formats. And he's here today to tell us about CMS's nano AOD format. Canonically, how do I fit physics into 1 kilobyte? So I see you're sharing your slides already, Andrea. Please take it away.
Okay, thank you. So I'll try to say something with some reminder or perhaps some introduction about what NanoD are for people that have no clue and didn't hear about that earlier. And then I'll say something about the experience that we gained with this thing in the past couple of years. And then say something about what I think could be the road ahead. Now, let's start with a brief history, and perhaps I can put some more introduction to that, because I'm not sure the background of the audience. So the data, the analysis in LHC experiment, in particular in CMS, changed a bit with time between the various runs, from run 1 to run 2. So between 2010 and then 2020, let's say, in the past 10 years. And the idea is that in the beginning, in run 1, there was some part handled by what we call the central production, which takes care of everything from taking the data from the DAQ up to reconstructing the data, calibrating the data, and producing some data sets that are used for analysis. And at that point, the central production was finishing what we call the AOD, so the analysis object data, or some description of the objects that want to use for analysis, or reconstructed particle, reconstructed objects. So, and the idea at that time was that the only analysis tool that existed was what we called PAT, so the physics analysis tool that was provided to do some calibration of the object, or perhaps to run some high-level algorithms like tagging, or some identification of some objects and discrimination between background and fake objects and real objects or things like this. Then this was in between run 1 and run 2. For the beginning of run 2, we developed a new format, what we call the mini AOD format, which has the advantage of being a factor of 10 smaller in size per event, which was running already some of those physics analysis tools, at least the most used one, the most relevant one. And the idea was to try to cover with a single format, with this reduced format, a large fraction of analysis, or order of 80% or so. And eventually this number by the end of run 2 reached well above 90% and it's still growing, because even some very special use cases for analysis that are currently needing to go to the AOD data tier are now covered by linear. And then at that point, or if you want at this point, some n tuples, lightweight root n tuples were created from mini-AD by individual groups. Now, to put things in perspective, an event in CMS is, a raw event is order of a megabyte, and similarly a reconstructed events. And then when you get to mini-AD, we are talking about 40 to 50 kilobyte per event. Now, at the end of run 3, at the end of run 2, we started developing, or during run 2, we started developing or even a common n-tuple format. So we were thinking if there is really a common base that we can have and can be widely adopted for run 3. The idea was to develop something which will reduce by more than an additional order of magnitude, or at least an order of magnitude. And we get to the ballpark of 1 to 2 kilobytes per event. That basically will contain everything that you need to do the analysis, everything that you will put in your n-tuple or so. And the idea clearly is that these will not be able to cover a large fraction of analysis like 90%, but perhaps we can do 30 to 50% with the first iteration. And and still having the possibility to do many of the choices that you do at the analysis level, so without forcing too many choices already at that stage. One important point in designing both the mini-AD and NANOD format is that many of the cuts and choice and thresholds that we apply in analysis, especially in a community like in a C experiment where you have hundreds of analyses. Many of those choices are, equally good or equally wrong, and they're just there historically. And people, compared some distributions and decide to put a cut somewhere, and that cut, it's not terribly different. If you place it 10% higher or 10% lower, you get a slightly different point in your efficiency, perhaps, versus background rejection. But and the idea is that they're not so different in the end. In fact, they're not different at all when you compare the final outcome of the analysis. And so we try to make some of those choices, at least the ones that are good enough and are common, that are shared by many analyses. And by doing so, we could reduce a bit the size. So here I may use those names again. So the raw, I really mean the data as it comes out of the DIQ. With RICO, I mean the reconstructed data containing all the physics objects with many details stored, like the calibrated hits or aligned hits, or even low-level reconstructed quantities that are then used to build the higher-level objects. With AOD, I just explained what I meant, and this is currently in CMS is simply a subset of the previous format. So you can obtain AOD from RICO basically with a vertical slicing, like removing just column or removing stream with the language of the previous talk. Instead, when you move to mini AOD, here it's really not a subset of AOD, it's sort of processing of AOD, but it's still in a C++-like format that is used by the CMS framework, what we call the event data model object type, so the EDM format. And on the other hand, as I said, NaNoD are really fundamental type, like arrays of ints and like root flat n tuples, if you want. So if you compare mini-AD and NaNoD, in mini-AD, we basically store things such as a vector of muons, where muon is a C++ object, and we may have multiple muons, so we store a vector of muons. Whereas in NaNoD, we may just store some columns that are attributes of the muon, and then they have aligned length when they refer to the same object. So if you have a muon, this will generate several columns, all with the same length within the event. So if you want to compare visually the reduction that we introduce, and you do it with pictures, I'm not sure if Zoom will compress the top left images to the level of the bottom right. I hope it doesn't. If you look at if you click on the link and check. So basically, if you compare with an event display, which has the size of the AOD, it looks something like that. And then if you compress to mini OD and to nano OD, that's the kind of quality you will get by simply compressing a PNG to that level. So this is just to have an estimate of what we do. Now, this perhaps I should have put earlier, given that some of you may not really be familiar with LEC processing, but this is somehow the analysis model in CMS, which is not exactly the same, for example, as in Atlas or in other LEC experiments. So the idea is that we start from the raw data taken from the detector, and we process it with some central processing, which is slow. I mean, it takes order of tens of seconds or minutes per event. And we can afford to do that about every 2 years or so, and I mean, to redo it. And then this creates some output data sets that are the RICO and the AOD. At the moment, we are not even storing the RICO anymore for the bulk of the dataset production, because it would be too expensive. We only store the AOD. And in fact, in the future, and even now already, we are migrating those to tape. We can't afford to keep all the AOD on disk all the time. So we may be rotating between tape and disk already. And then a couple of times per year, we could afford to do the mini OD, so to produce this additional step. Clearly, when we want to do so, we need to pull on disk the AOD that are needed. And then in principle, up to every few weeks, but currently up to every few months, we're doing the mini to nano step. Now, how do you get to analysis? You may need to access information that are at all levels. So our hope is that we increase the fraction of the analysis that only need these last 2 stages. And at the moment, we think if something like 50% can work out of NanoD, another 40% on top of those 50 or so can come from mini. And the idea is to cover with those 2 formats up to 95%. And then we may have only a few percent that need to access read information that is either really in raw, RICO, or AOD. And for those, we have some special jobs that we call spin jobs that are more tailored for individual analysis, and they may do some selections and pre-process the information, and they will run together with the RICO or together with the mini OD. There will be some pieces of very specific of some analysis that are still run in the central production. So this way should be able to cover all the various use cases. Now, the content of the Nano D is clearly, there are things that we cannot afford to store. For example, we cannot afford to store all the tracks that we have in the detector in this budget. And in fact, this is not even needed, in the sense that most of our analysis, beside a few that are really in these categories here, do not need at all to look at the details of every single track. They may need details of the tracks for few objects like the leptons that are more interesting in LEC, but then this is not hard to store more details for just a few of those objects. The biggest thing is the jet collection, and the jet collection is made, if you can see in this table, of order of 10 objects per event in average. And the fact that, I mean, for jets, we store many variables up to, you can see here, we store 50 variables. And then in addition, you may want to store all the variations due to systematic uncertainty of those variables. For example, the energy may be changed when you change when you want to estimate the calibration. So if you have uncertainty on the jet energy, you want to have also variations up and down. Now, in CMS, we have something like 20 or more than 20 variations for which we have plus and 1 sigma and minus 1 sigma. So you will be storing 50 copies of the energy and perhaps 50 copies of the mass of a jet if you will do so. And so we avoid doing that because this is some kind of information that you can in principle recompute on the fly. So just storing the jet information and a couple of other variables, the momentum information, a couple of other variables for a jet, you can recalibrate the jet. So we don't store persistently those. And the idea is that it will be computed on the fly by the analysis, it will be computed on a subset of the events that are interesting for some analysis. Similarly, we reduce the gen level description to the very minimum. So we do not store all the final state stable particles, but we try to store important particles from the MC truth. So like matrix element level information or flavor information. And then we can add information which is specific for a few analyses. It can still be added as long as it is cheap. So basically, if some additional analysis level quantity is needed, you can try to compute this ratio, see how much additional size will that introduce, divide it by the number of analyses that that will exploit and that will use this additional information. And if that's less than a few bytes, then it's something that makes sense to go in. I mean, you can consider that in CMS, we have about a few hundreds of active analyses at any given time. And so for an event size of, let's say, 2 kilobytes, it means that you have a budget of order of 5-10 bytes per analysis. So some additional features. Now, this is a bit technical. There is no cross-cleaning, meaning we don't throw away objects at the level of NanoD, because this is something that can be an analysis choice, but we instead do the linking between the object, especially we do the kind of linking that is not possible to do later. So you can say the two objects are basically the same due to the same footprint, but they're, and so only one of the two really exists. So you may have that some information in the detector can be assigned to being a jet or to be an electron. So you need to decide in the end in your analysis if that's an electron or a jet. And so you need to throw away one of the two. But the criteria that you decide which one you want to take may very well be dependent on the analysis you're doing and what's the final state you're looking for, what's your background or what's your signal. And so you can always do this cleaning and this linking and then cleaning with some angular separation. So checking objects that are close by, and if they're close by, you throw away one of the two. But there is another way, which is looking at the constituents. In CMS, we have this the particle flow algorithm exploited. So basically, every high-level object is built of some particle flow constituents. And then you can do the checking if objects are sharing particle flow constituents. If they are, you link them together so that downstream, when you will do the analysis, you will know that you need to do the cleaning. And this kind of checking the constituents is not possible anymore in NanoD. I mean, after you throw away the information. So you need to do it, you need to do the linking when you create the NanoD. You cannot do it after. Okay, one last thing is that there is a set of tools that also is provided. It's called NanoD tools that is used to do some kind of fastish scheming and also to compute some corrections. For example, the jet energy correction uncertainty I was mentioning before, or doing some jet smearing, or computing the tagging uncertainties, or lepton scale factor and so on. So there is a set of tools that come with the NanoD, but this is not mandatory to be used. I mean, there are you will hear other tools that are that can be used for that. And now the reason I say is because I'll show in a moment the popularity of these tools, and this is somehow a lower estimate of the usage of NanoD. Last thing that was also touched earlier in the other talk, is the documentation. Okay, so for such a high-level format, it is really hard to try to figure from the code what a given variable is. So you will need to navigate back a couple of steps, because to understand what this variable is, you may need to get back to the mini-OD, and then you also need to understand how in the mini-OD was created, then you get back again and again. So rather than trying to dig the code and understand, the point is that we have a one-line description of what that thing is, which lives with the variable itself. Is basically in the documentation of the TN tuple. So clearly, this is not very complete description, as you can see here. Okay, but it should be good enough to understand and resolve any ambiguity that people may have. I mean, so if you are an analyzer from some CMS, the thing that you want to understand, if here you read the muon IP 3D, well, you understand probably that that's an impact parameter 3D, even from the name. The additional information that is written here is that it is with respect to the first primary vertex. And so it could have been with respect to the beam spot. And this is an information that is written there. And probably if you want to dig this same information from the code, it will take some time, and you will need to to look back several iterations in the C++ code before you can get an answer to that question. Now let's get to our experience with NanoD after a couple of years. So it has been introduced at the end of run 2. So most of the analysis efforts were already ongoing with some existing framework and tuples already set up. And so as I also said in the previous talk, there is no reason to switch when you already have something, unless really you have great benefits. In addition, the initial central production campaigns were more for testing than for actual usage. And the content we had in the beginning was missing some stuff that was easy to fix, but still we needed to have that added. And because at the time, there were not that many production in the very first years, I mean, clearly people prefer to remain with their own tuple if they already started them. Then, I mean, still some people started adopting the format and many did it with a few private changes and adaptations that, I mean, first they are expected, and then eventually they can be contributed to the central common format. But still, we anticipate that people may want to still adapt the NanoD format and produce their own NanoD format, for example, for a small sample like signal sample, or even in other cases. And it is still useful to generate your own format starting from a baseline which is shared, where 99% of the context is shared with other analysis in a way that any problem, calibration, or any non-feature is understood. The important point is that this doesn't lead to some divergence in the end, and that everything that can be eventually centralized is put in the common format. Now, a survey has been performed in CMS with a Google form that was filled each time an analysis approached the physics approval. And so I tried to look through that and try to understand a bit how things evolve. So now, in the past year or so, more than 30% of the analysis used at least, I mean, also let me say NanoD, because some of them they're using NanoD and as well as MiniOD. This because in many cases, many analyses have some multiple groups that are cross-checking each other, so they may have used different formats, or some analyses are in fact the merging of multiple, let's say, decay channels or production channels of the same processor, so performed by different groups, and then again, different groups may be using different toolkits. Now, this is the plot of how, if you integrate from each date 6 months back in time, how many analyses reported that they are already using NanoD, and this is about 30%, or in red you see the one that are either using or planning to use for next iteration, because, for example, they say, I had already my n-tuples for run 2, but for sure at the next round I will switch, and this is above 50%. And then if you also add those that say, well, I may use, I mean, I see no showstopper, I didn't think really about that, but in principle I could use, you get to 80%, which is definitely a number which is too optimistic in my opinion. And another index to understand the popularity of that is looking into how many forks of the NanoD tools repository we see. Basically, if you want to use, can you still hear me? Because my mouse got stuck.
We can hear you fine, yeah.
Okay, so I keep talking, but I don't know if I can switch slides. So let's see if my computer, yeah. Okay, it's probably back. No. Can you hear me now?
Yeah, we can hear you fine.
Okay, now I can again see my mouse. Okay, so I was saying this tool is just used to calibrate and to post-process the NanoD, and it's not needed, but if you want to use it, most likely you want to clone to make a fork on GitHub. And you see that the number of forks was steadily increasing in the past 2 years, and we now reached about 200 forks. Now, another point was, okay, we need to create this format pretty quickly when we have changes or when we want to make a new iteration and so on. So the idea is that people are expected to add some new observables and get N-tuples back with that in a reasonable amount of time, which is competitive with what they will do, what they will achieve by doing it themselves. And if they do it themselves, we may take today basically 1 or 2 months to make a complete production of N-tuples from mini-OD running on the grid and so on. So what we check is that we can produce them quickly. I mean, the CPU time is not really an issue. And even the handling of the large number of data sets and large number of events that was initially a bit more of an issue, because submitting hundreds of thousands of processes on 100,000 data sets was a bit of stress for the production system, but in a very short time, I mean. But this now works pretty well, and we show that we can produce in 1 or 2 weeks 50 billion events with no problems on the production grid of CMS. Now the idea is that the frequency of that still is expected to increase for the future, and perhaps we want to have some more on-demand policy than some scheduled time. But we see at least no showstopper from the technical side. The other problem is a bit more sociological, is the time that is needed to develop new features, to validate them, to agree on what are the features that are a must for a given campaign. And for these, we are setting up various tools for continuous integration, and we have a dedicated group following basically these in CMS. Okay, got stuck again. I'm sorry. Can you still hear me?
Yeah, your sound comes through very well. I don't know what's wrong.
Okay, but I don't know why. Probably there is a Chrome instance that is getting crazy. Okay. So, can you still hear me, or you hear me twice, or?
I can still hear you. Yeah, that's no problem.
Okay, then I'll try to share from these other. Okay.
We just got some horrible feedback from you, Andrea. And your tab died. Andrea, I had to mute you. There was like really bad feedback that happened there. Also the quality of
thank you, Grammy, because I was not able to, as the other computer got stuck with the mouse, I cannot mute myself on the other.
Right, okay.
So that's exactly what. Okay, I'm sorry, I'll just get back to the slides in a second and share the screen from there. Yeah. Can you also...
Do you want me to stop the sharing?
Yeah, stop me sharing on the other computer if you can.
Yeah, I think I did it.
Okay. Okay. You should see again the slide.
Yeah, we can see you and hear you well now. So.
Okay. Okay, so now some more experience we gained during run 2. One thing is that event weights are a pain. That in the end, we have way too many. For example, for PDF variations, we have hundreds of weights per event. And it's not even clear that we really use them all the way in the analysis. So those were really a problem to handle. There were also plenty of bugs. When you try to standardize the usage of those weights, you figure that each generators describe them in a different way. So we had many trouble. But now we are a bit converging, reducing the precision and trying to do such that we can store those. Now, another problem is that too many people use a format like NanoD, even those that cannot really make it with a few kilobytes per event. And those should probably use mini-OD. Instead, sometimes they try to, try to get back all the tracks into this format, which will will kill the point of having such a small format if in the end you get the same size of the previous data tier. And then another problem is that many machine learning applications may want to really see more raw features like the stuff that is in mini OD rather than in nano. So the idea is that you will need to train on mini OD and then save the output on the nano D. And even if some machine learning applications are often taught as analysis level stuff, then you may need to use mini OD for some of those to really work. Another thing we learned is the nano OD tools is not really satisfactory. It has a kind of a Python event loop based, so this is slow by design, but it has some pre-skimming, which is made with T3 draw-like syntax. So you can, if your analysis can select only a few events, it's fast. Otherwise, it is not. And clearly, Cofea that you will hear in a second, and other data frames that can go much faster than what nano OD tools does. So the idea would be to have some C++ module to compute the uncertainty and to do the kind of things that nano OD tools are doing right now. So that's one of the things we learned. And then the last thing is that with nano OD, we open the possibility to create analysis facility, because basically we can store full data sets in this format into basically in a single SSD drive of 50 terabytes. So it can definitely fit a local cluster or even in some cases a single multi-core machine. We have additional customization that we're doing for specific purpose. For example, we have nano D for some calibration workflows, or we have a special analysis group that, as I mentioned, they may want a small format similar to nano D, not necessarily nano D. And as I was mentioning, the common base, even for example, in the calibration, in the context of calibration, is really useful because it means you can take analysis quality selection into the workflow for physics object reconstruction if the calibration data sets are sharing some common base with the analysis data sets. And yeah, and we are also looking into nano-like formats for example, for B physics, which has a completely different set of needs than many other analyses, because they need tracks for fitting, even soft tracks. They need particle ID, secondary vertex, and the idea is to investigate if a format like nano D for B physics is possible. So in conclusion, nano D format seems to work as we expected and planned, and I mean the adoption in run 2 is in line with the expectation. I'll say the plan is to boost that for run 3 to increase the coverage by extending the content. In fact, in principle, even if we will double the size of the nano D, it will not change much in terms of our computing model, because the footprint is still pretty small. Still, it doesn't mean we want to double the size for serving just the use case of a single analysis or something like that. We'll try to keep the philosophy that I mentioned as a rule for adding stuff into there. And then we want to increase the frequency and make easy the additions of new observables into these, and also to improve the automatization of the validation workflow and preparation of new cases. Okay, that's it. I'm sorry for the technical troubles.
Yeah, no worries, Andrea. We got there in the end. Thanks. Great. So I can now open the floor to questions. Kolja, you've raised your hand, so go ahead.
Hi, Andrea. Yeah, just out of curiosity, you kind of mentioned it a little bit on the previous slide, but what about heavy ions? I mean, I'm pretty sure that they don't fit the nano AOD format.
No, they don't.
Is that something similar?
Yeah, no, at the moment we managed to get to something similar for mini OD, and also that took some time with some customization, because clearly the use case is completely different there. Now for heavy ion, I think we will need to go a similar direction as for B physics. So really think about what can be common to the common format and what instead need completely different design. And probably we'll need some heavy ion expert to try to figure if there is a common set of variables that are basically used in a superset of variables that are used by all heavy, or the most heavy ion analysis, and try to see what would be the footprint of that. Now, we should also say that in CMS for heavy ion, we have many samples and so on, but they are not as large as the rest. I mean, or if you want, they are somehow on a different budget. Let me put it this way in terms of the size. When you change the AOD or the mini OD or the nano OD for the PP data, this is immediately reflected into tens of billions of events. So it's a bit, we need to be a bit more careful in that sense.
Thanks. Time for another question. Maybe I'll just pitch one in, Andrea. What's your experience with how groups use these? I mean, do people try and download the set of nano AODs that they need and run on local resources, or are groups submitting batches of jobs onto the grid and letting the grid handle finding the data for them as needed?
I think there are multiple access patterns. I mean, one is definitely that you use the nano OD tools on the grid to reduce, to basically reduce the number of events by, let's say, what we call skimming, and at the same time increase the size per event by adding some calibration, some uncertainty, some additional things that you may want to compute once and for all. And then they get back to their local machine, something which is factor several reduced and also limited not to all the samples that we produce in CMS, but just for the samples that are relevant for an analysis. Another use case is that people may have on some larger site, they basically a full copy of the nano D, and they can even access that directly. I guess you will hear more in Matteo's talk about some access patterns that are possible with the. I mean, these new tools like Uproot and Cofea and our data frame really allow us to also directly process the full data sets. And we have an example of that. You'll probably hear from Cofea, and similarly, the WMAS analysis in CMS is accessing a full nano D sample of several billion events with our data frame, with this massive parallel processing without any additional intermediate step running, for example, on a machine which have 100 cores, and so they just use the multi-threading in there.
Grand, thank you, Andrea, but I'm afraid I'll have to close the discussion here in the interest of time. And let's move on to Matteo, who's going to give us the last talk of today's meeting.
Yeah,
Matteo,
hi.
Hi there. Yeah, we can hear you well. Do you want to start sharing? And I'll just introduce you as you did your PhD at the University of Oxford. And since 2015, you've been working at Fermilab as a research associate with CMS. And now you're working in the team developing new approaches to do analysis, exploring these columnar and declarative ways of working. So Matteo will be giving us a talk today on columnar object framework for effective analysis, COFFEE. And I'll let you take it away, Matteo.
Okay, can you see it in full screen?
Yeah, we can.
Okay, so thanks for the introduction. So hi everyone, I'm here to give, let's say, a high-level description of this project that's called COFFEE. COFFEE stands for Columnar Object Framework for Effective Analysis. We started this back in 2018 with the idea to try to see if we can shift a little bit the way the analysis approached in high energy physics and possibly get a speed up. So as I said, I mean, this description is going to be kind of high level, especially because the main message that I wanted to convey is that this project works considering which are the constraints, and constraints are not always only technical, but sometimes also rather sociological. So I'll try to see if I'm able to properly describe this aspect of the project that, in my opinion, is one of the most important. You will see that I will repeat here and there some of the information that you have already heard in the previous talks. I'm sorry for that, but I still think it's a worth repetition exactly for what I've just described. So let's get started. I mean, we are all familiar with this, right? So this is the way the scientific method is applied in energy physics, but not only in energy physics. So we will always want to compare.
Neil, I'm still on your title slide.
Okay, so this is
things are not advancing properly.
This means that it's getting slow. Let me know when it changes. Otherwise, I'll I'll switch very quickly to, let me switch to PDF, sorry for that. I'll quickly stop sharing just for a second. Let me pick up the PDF version and share again. Let me see, where is that? Can you see it now?
See the PDF, yeah.
Yeah, let me see if I can put it full screen. Where is the button? Sorry. Oh God. Yeah, I'm supposed to be smart, right? That's clearly not working.
Use a green. Try view full screen.
There we go. Sorry. Okay. Do you see the slides changing now?
Yeah.
Yeah, that's good now.
That's great. So as I was saying, I mean, as everyone in science, at the end of the day, what we want to do is compare predictions that derive from hypotheses and test them in the real world, right? We do that in energy physics by comparing simulation based on theories with data that we're able to collect from our devices. And this is a plot from the 2012 discovery of the Higgs boson, where you can see exactly that. So this is a clear visualization of how the scientific method is applied. At the end, so therefore, what we want to achieve here, we would like those black dots and those color curves to appear as soon as possible in the form of a plot, to have a visual and statistical comparison between the two of them and possibly claim discovery. In order to do that, usually both detector data and simulation are handled in a centralized fashion, and something that is called offline computing. That is a large group of very expert people that really care about getting detector data and simulation processed as soon as possible and as correct as possible. What happens after is usually left to individuals. So definitely you need some sort of analysis software to make these comparisons and produce these plots. So the big difference here is really how is handled inside the collaboration. While the first part is centralized, the second part is really left to the individual. And let's just give some quick numbers to describe which is the context where this happens. These are usually large collaborations. I'm a CMS member. Similar numbers are for also the Atlas experiments, so other large collaborations that work at the LHC. We're talking about thousands of particle physicists from hundreds of institutes for more than 40 countries all around the world. Central production handles large volume of both data and simulation, and talking about billions of events. And usually a grid computing model is used. So CMS, these numbers come from CMS. We have 300,000 CPUs available over 70 plus sites spread all around the world. And when we speak about individual analysis, roughly inside the collaboration, there are more than hundreds of teams, all using different analysis codes. All these codes doing more or less the same things. There is almost a one-to-one correspondence between a published paper and a PhD student. And I believe that this is an important point to make, because analysis is usually led by the most inexperienced person. And it's not only the most inexperienced from a scientific perspective, but most importantly from a technical perspective. So the person that really writes code is usually the one that has the least experience in writing code. Speaking about data volume, we all know that extracting physics results require to handle large data sets. In round 2, we are talking about hundreds of petabytes, and these will increase to exabytes in the next decade. So with the planned high luminosity run of the LHC, this is exabytes is what we are expected to deal with. So we can imagine that inefficiencies in the way we perform that analysis may result in a waste of storage space and large time to insight that is already days to weeks to run an analysis with the most common tools available to the collaboration. That therefore with larger data sets, we are not expecting this number to go down, we are actually expecting this number to go up. And since storage space is already, I would say at limit, is already a concern, we cannot afford to waste it in the next decade. So all these problems that we expect at a luminosity to appear, of course, as harder to be solved, are already there, and we are already feeling their effect. Where does these inefficiencies come from? So on this slide, you can see on the right part a sketch. This is just a visual representation on a typical analysis code that involves several different steps here. So you see a first step of entabling that has been mentioned already in the previous talks. This usually happens because each and single analysis group has their own needs, and therefore from a centrally produced data format, usually in root, there is a step that does not really reduce the size, but it manipulates the event content in order to produce those variables and those quantities that are needed for a specific analysis or group of analysis. Then, since the size is still too large to allow for a quick analysis, there are several steps, at least one step of skimming and slimming, where really the idea is to reduce the total size of the analyzed inputs so that latencies go down. And usually the reduction in size is of a factor of 10. Up to that point, when you have very specialized analysis entables, then you can, on your laptop, make plots every few minutes. That is, of course, good. It goes into the direction of being really interactive, but at the price of a huge amount of work. If, for example, you need to tune analysis cuts, so you have to go back one step, let alone if you need to include one more variable for your analysis, then you have to go back 2 steps and pay the price of the large time that you need to pay for that you need to spend for producing the other 2 intermediate outputs. So time to insight is, of course, a problem, and interactivity, I would say, is a problem. But there is also here inherently a problem with storage space, because each and single step produces intermediate output. So you're going to write on disk other entables. We can ask ourselves why this happens. Well, I mean, this boils down to using for analysis a computing paradigm and tools that are very efficient and useful for central production. But here we want to use it in the context of individual applications. So this, let's say, inconsistency creates this very convoluted way of using these tools, and therefore resulting in a convoluted way of performing analysis. So which is this convoluted way? Well, is something that we all know well, right? It's performing, if you want to use root for that analysis, eventually you're gonna have to perform an event loop. Root is a file-based data representation. So each file is a collection of events. So what we want to do, you want to loop over files and over events in file, and at each and single round of the loop, you're going to load values per event. You're going to evaluate several expressions. You're going to store the output of this computation in a different root file. So as I mentioned before, you are gonna stage out intermediate output, duplicating actually the quantities that are useful for the analysis but that have not been manipulated, and then you repeat, and you do this each and single event. Here is where we enter coffee. So let's first answer the question, what is coffee? It's a package in the scientific Python ecosystem that gives users, high energy physics users, the capability to interface with columnar analysis. So you see in this sketch here, this is a sort of a visual description of the Python ecosystem, what you can find out there, the different packages and libraries that serve different scopes. And you see where coffee plays itself. So you have a little bit of coffee in algorithms and a little bit of coffee in visualization. And we'll see later on how actually coffee achieves these two scopes. What coffee does, it gives the possibility to have a shift in paradigm. So to move from an event loop analysis to what's called columnar analysis in the data science world. It first starts from, in some sense, changing the data representation. So we go from a file-based root data representation from representing high energy physics data in columnar fashion. So in this case, what we want to do, we want to load values from many events into contiguous columns. So we are sort of creating a big table that represents all the data that we need. And in this representation, rows are events. Once you have that, you can perform columnar analysis using array programming expressions. So instead of looping event per event and computing the same operation over and over again, you are now ideally applying a single vector operation over all columns. That means that you are applying that operation over all the events simultaneously. And in this case, you kill the inefficiencies that come from writing explicit loops like you're forced to do in an event loop analysis. What you can do then, you can store the right values in contiguous columns. In this case, it's like you are adding additional columns to the original table that is the representation. That is the columnar representation of your energy physics data. In this case, you can handle the problem of keep duplicating data and keep writing on disk intermediate output. In this case, no new files is going to be written. So which are the main benefits of approaching data analysis this way? You will see that here, more than all these three bullets are rather sociological than technical, as I was explaining before. So benefit of ease of use and readability goes into the direction of allowing least experienced people to write better code. So code is human readable. That means that this is because columnar analysis is a higher level description of manipulation. So you can really see when you read code what the code is doing. So for a newcomer, it would be easier to pick up a code and understand what that code is doing. And I anticipated myself by already mentioning writing efficient code. Again, if this product is to be used by people with limited experience in programming, you care a lot about providing a tool that can limit the inefficiencies that an experienced coder can put in his or her code if it's written with a more complicated approach or with a more complicated language. So taking advantage of the fact that columnar analysis aligns with the strengths of modern CPU, using a columnar approach make it easy to write computationally efficient code. And last but not the least, there is community support. So Coffee takes advantage of a lot of the tools that have been widely used in the data science world, and community support is crucial for the quick resolution of problems, of error messages, of crashes by simply Googling them, you will find a large community of people that can provide a solution by simply reading posts on Stack Overflow. This is an important aspect to, in this case, not making the code efficient, but making your own time you spend coding more efficient. So what Coffee provides, because one can tell, especially based on the last point, well, if you rely completely on tools and libraries that are already out there, what is Coffee doing? Well, Coffee is putting all of them together in a way that is physicist friendly. It fills the holes of things that are specific to their analysis in energy physics that of course are not covered by other Pythonic libraries. Coffee implements typical recipes that are needed to operate on NanoEOD-like cantables. So I'm glad that the previous talk was describing the NanoEOD format, so that it allows me something that otherwise would be CMS jargon to make the point here. So there are specific tasks that we need to perform efficiently in order to do their analysis in energy physics. One of the most important being the application of weights that already Andrea hinted at the possibility to apply them on the fly, right? So instead of having shifts and systematic variations already computed in something that is NanoEOD-like, that makes his size larger and larger, those can be computed on the fly. And Coffee provides the tools to do exactly that, to apply weights and Monte Carlo corrections while you run your analysis. And Coffee also supplies facilities for horizontal scaling. So here, essentially what I'm saying is that Coffee allows to run your analysis on scale-out systems like Dask, Spark, Parcel, of course, HT Condor. So taking advantage of the parallelization offered by the scale-out system in order to speed up the analysis turnaround time. As mentioned before, Coffee is a Python package that is pip installable, and again, is realized using libraries in the scientific Python ecosystem, or better saying, it relies on libraries in the specific scientific Python ecosystem to operate. It uses a very clever columnar data representation that's called awkward array, that is provided by the awkward library as described at the next slide. So this is, I think it's the trickiest point from a, let's say, philosophical perspective of applying a columnar analysis in energy physics. The fact that energy physics data is not inherently rectangular. You cannot put energy physics data as it is and throw it in a table. And the reason is very easy. You don't know event by event how many particles and which type of particles you're going to produce. You may have an event like the one on the table at the bottom left, where you have 3 muons, and the second event has only 2. And therefore, if you're going to put brutally, with brute force, energy physics data in a table, you're going to have a lot of holes, right? So the idea is actually to represent energy physics data as arrays of variable length arrays, so jagged arrays. This jagged array data representation, as I mentioned before, is provided by the awkward array library, and it can be visualized as represented here on the bottom right of the slide. So you're going to have an array of subarrays that represents your muon PT. So again, here we're representing only one feature of the muon particle, that is its PT, and it's going to be treated really as a column in a table. The only difference is that you have subarrays, and each subarray is representing an event. But you can still treat it as an array, and therefore you can apply all the array operations that you want to perform a columnar analysis, to use a columnar analysis approach and operate on all the events simultaneously. And here is one example on how you can operate on all the events simultaneously in the context of applying analysis selection, that at the end of the day it's the key aspect of performing analysis. We want to select event, right? And the way to do it is represented in this slide. So you see that you have the array from the previous slide representing the mu-MPT in all the events. You can apply a mask. So a selection here is really a mask. It's really another array that has the same shape of the mu-MPT. It's an array of true or false, of booleans, that are constructed by making a requirement on the mu-MPT itself. So when you pass this mask to the original array, you are gonna select only the events that show a mu-MPT that is larger than 30. So you can see that here there is no explicit loop whatsoever, and the mask is applied to each mu in each event simultaneously. Coffee provides a couple of classes that help describing and executing your analysis efficiently. Let's start from the coffee processor class. That is an abstraction that can encapsulate the analysis code. So here, using an analogy that is really offered by the fact that this project is called coffee processor, you can see it like a coffee pod that you can in principle use in different coffee machines. So the coffee pod is representing your analysis. So everything that is the definition of the analysis selections, the application of the weights, and the definition of the output histograms is encapsulated in a coffee processor, so that you can keep it separate from the way input columns are delivered and the way the output is reduced. So you here on the right part of the slide, you have a sketch of how a coffee processor can be written. And you have in bold physics goes here. So that's where you're gonna define your objects, you're gonna apply your weights, you're gonna apply your selections, and you're gonna describe your histograms. As I said, this is the definition of the analysis in the form of writing a coffee processor. It's kept separate from its execution. Therefore, coffee offers another class that's called coffee executor, that really handles the interaction with the delivery system, the column delivery system. And as I mentioned before, coffee offers the possibility to use different backend scale-out systems. It currently supports Dask, Spark, Parcel, and HT Condor, where Dask is the most advanced scale-out system interface with coffee. But that means that once you have your processor, it can really be shipped around and executed on different executors with a single line change. And I think that the sketch in some sense is self-explanatory. It's a sort of a representation of how the map reduce concept is developed and applied in coffee. And since NanoD has been described, and since coffee started from a group of people working on CMS, we paid special care in including utilities to interface easily with the NanoD format. So in nano events, in coffee, you will see, you will find nano events that essentially encapsulate the typical schema of an NanoD, so that it's able, coffee is able to interpret NanoD files appropriately, meaning that it's able to recognize which objects are physics objects and has to be treated like Lorentz vectors. And it keeps all the cross references that Andrea described before, for example, for cleaning jets from muons, or better saying, from particles that share the same PF candidate. So those cross references are preserved in coffee in the form of the schema implemented in nano events. So this makes writing code very, very easily, because you can see that you can instantiate event objects by simply reading an NanoD file. So you define at this line here, you load all events by using the from root function in Nano Events Factory. And but at that stage, you have everything available in that Nano AOD and provided to you in the form. For example, if you would like to retrieve the energy of genjets, you simply do events.genjet.energy, and you will have the jagged array that describe the energy of genjets in all the events. So already interpreted as an energy in a Lorentz vector that is the genjet in each event. This leads to a quick processor code example. So before it was only a sketch, here is a real example of how easy it is once you rely on the different concepts and classes implemented in Coffee, and once you rely on this nano events functionality to write an analysis, a quick analysis in Coffee. You can load information of the electrons using the nano events functionality that I just described, and you can mask them the way I described before. So you can write a big mask like the one that you see here, placing requirements on different qualities of electrons, and then you can apply this mask to filter electrons with no explicit loop over electrons, and use a requirement on what you have just defined as a tight electron to define an event selection in this case without any explicit loop over events. Coffee has already been used by several different CMS analysis. We have order of tens analysis in CMS that have already started adopting Coffee. The user community is growing. We are up to 50 people contributing at some extent. People decided to use Coffee in creative ways, I'd say, but there are some analyses that use Coffee for its original purpose. So to analyze CMS data directly from centrally produced NanoD, going to plots with no usage of standard tools. So for those analyses, we, let's say, measure performance in terms of human time saved, so not really CPU time or bare computing performance. Results were encouraging in the sense that no intermediate output is written on disk, and as I mentioned before, this is one of the concerns moving forward. You don't want to wait this space, but most importantly, I'd say the turnaround time, speaking about the human time that it takes to complete an analysis, is reduced by the order of magnitude. So you reduce from days when you have to go from centrally produced data formats to plots with that convoluted analysis scheme that I described before that involves several different steps of skimming and skimming. Now using Coffee in one go directly from centrally produced NanoD, it takes hours to get to plots. So in conclusion, we believe that we put together an innovative tool that helps high-energy physicists to perform columnar analysis, and it actually Coffee pioneers the utilization of columnar analysis in high-energy physics. It goes into the direction of addressing some of the main issues that affect the way we currently do analysis, namely shortage of disk space and long time to insight with limited interactivity. And in some sense, it's a real-world solution in the sense that it takes into account all the constraints, and as I mentioned before, not only technical constraints, but also sociological constraints. And it's encouraging that it's already been used for publishable, if not published, results. I'll leave you with links to documentation and other interesting stuff. So you can access documentation from the GitHub repository of Coffee. You can see examples of the application of Coffee to solve some benchmarks designed by Iris Sepp that are tasks that help demonstrate and compare usability of different analysis tools moving forward for analysis in the high luminosity era. As I mentioned before, we have a growing user community. If you're interested in joining, there is any group that you can join and a bi-weekly meeting to attend. And with that, I thank you again for the opportunity to present coffee today, and happy to hear some questions. Thank you.
Thanks very much, Matteo, for that very complete overview. So Jan has had his hand up very patiently for half the talk. So go ahead, Jan.
Yeah, so I didn't quite get, so if you have some quantity which you have multiple times in the event, how do you handle this? Like, I don't know, a series of hits or a series of tracks. How do you handle that in the columnar storage?
So as I said, it's the way we represent data is as an array of subarrays, and this can be as nested as you like in some sense. So I showed only an array that is mu-PT that has one level of jaggedness, right? Because you have different.
Yeah, but you're talking, Jan. You're talking about the issue of indexing, or compression through indexing back into some flat array that contains all the data for a specific event, right?
Well, I mean that's one way to do it, right? No, the question is, right, the columnar storage, right? The storage backend, right? Does it have like an array type in a cell, which then has a more complicated substructure, or is it all simple types, right?
So it's, in this case, it is templated on, or sorry, the data store that we're using is nano AOD and root files. So it's simple types and arrays of simple types. If you go to the Coffee GitHub and look at the DAOD Fizz Lite pull request, this is an example of a much more, let's say, complex data type that a guy on Atlas is working to have ingested into Coffee. And that's where you start to see more interesting ways of handling repeated data or highly nested data. I'd point you to that for just a straightforward example in the code.
Okay.
But as far as like compression through indexing and things like that, all of that can definitely be handled inside of awkward arrays. So you just have to define the schema for it.
Okay, thank you.
That's right. And actually, this gives me the possibility to make a quick comment to tie back to Andrea's talk. We like a lot the nano-AOD format, or everything that is nano-AOD-like for this kind of operations. So for using columnar analysis, not that much for the reduced side, but most importantly because it's a flatter format that makes our life easier in extracting columns. And I believe that one of the biggest pains, if it's really the ability to efficiently extract column from nested files. So the fact that the nano-AOD format is flatter and less nested helps for this kind of, as I mentioned before, this kind of operations, the ones that you want to perform in a columnar analysis context.
Thanks for that extra clarification, Matteo. Claire, please go ahead with your question.
Hey, can you hear me?
Yeah.
Okay, great. Thanks. It was a great talk. Thank you so much. I actually appreciate your remark on analysis are done usually by the most inexperienced students, and they struggle. And I hope that this will actually be a way that people focus on the physics and the back end is done. Hence my question. How will the trainings be organized? Is it going to be analysis specific or a bit general so that other people, for example, June, can just jump in? How is this training insight for the future and for future?
Well, I'd say that's so far. First of all, yeah, I mean, I was one of the students, right? And I suffered a lot. And I actually was judged by my limited computing skills early on, and I didn't think it was fair, right? I was a student in physics. You should see my potential as a scientist, not as a programmer, right? The way we are approaching this is we are doing a lot of things. So I mentioned a growing user community, a bi-weekly meeting, but the core group of coffee people, coffee developers, are really heavily involved in you know, one-to-one chats with all the people that want to give it a try and start with the tool. We have multiple ways of contacting us. We have been having tutorials, so advertising and in some sense also teaching in the context of tutorials and analysis schools. We have very good examples you can start from. For what concerns trying to apply tools in different contexts, like for example Dune, there have been already some crossovers, I'd say, that happened really in the form of the core group of developers of Coffee working with some of the Dune people to see the applicability and the limitations and the bottlenecks that we may currently have. Moving forward, this is a personal comment. I believe that the fact that this project is heavily rooted in the data science world will make picking it up easier and easier as we move along and we try to really leverage the large overlap that we now have with similar applications, similar tools, and similar approaches in other areas, also non-scientific ones. Yeah. The community support is what you want to achieve, and at some point you want to really be self-sustained in some sense, where is the community that helps the teaching.
Yeah, I've got one comment on top of that. As far as like taking action and seeing an example of what training looks like, for the past couple of years, just within CMS and the LPC, what we've been running are these hands-on or hands-on advanced training sessions, or HATs, at the LPC that are CMS specific, but we can certainly get them material for those since they're already public out to you, and we can start to see how to change that for Dune or any other experiment. And I think we have a template from which we can make modifications and make it more specific to the experiment, and probably use that as a set of use that as pieces and parts of a training system in or training setup in a very different environment.
Thanks, Lindsay.
That would be great.
Yeah.
Thanks a lot.
And thanks for the question, Claire. I think we're going to have to close here because time really has run away from us quite a bit, but it's nice to end, I think, on underlining the importance of training. It takes us all the way back to Jan's original observation that we want to use modern C++. So we need to train people how to use C++ properly, just as much as any other tool that we come up with. So I'd like to thank all of our speakers and everyone that contributed to the discussion. And just to let you know that the next meeting in the Software and Computing Roundtable series will be in a month's time on Tuesday, the 6th of July. We'll be looking at analysis again, but a rather different take on it because Nicholas Wardle will be introducing, can we really reinterpret data from the LHC? So I look forward to that. And with that, I'll close the meeting here. Thanks, everybody. Have a good rest of the day, morning, evening, wherever you are. Bye-bye.